At ambient temperatures and without a corrosive environment, the life of a metal component in steady-state conditions may be unlimited, provided operating loads do not exceed the yield strength or fatigue limit of the specific metal and wear is not serious. But change just one condition, the temperature, and we have a different story. At elevated temperatures with a steady or fluctuating stress, the life of the same metal component is limited. At elevated temperatures, stress produces a condition of continuous strain. This is called creep. By definition, creep is time-dependent strain causing distortion. It occurs under stress. And after a period of time, the creep generated by elevated temperature may terminate in fracture by stress rupture, also known as creep rupture. Since the conditions under which creep and stress rupture occur depend also on the alloy, the magnitude of stress, and duration of time, elevated temperature failures can occur over a wide range of temperatures. For a given metal, elevated temperature is frequently considered to begin at a temperature equal to approximately 1/3 to 1/2 its melting point, measured on the absolute temperature scale. However, this rule of thumb does not always hold true. Actually, the temperature at which the mechanical strength of a metal becomes limited by creep rather than by elastic limit must be determined individually for each metal or alloy. Types of elevated temperature failures. The principal types of elevated temperature failures are creep and stress rupture. There is also low and high cycle fatigue, thermal fatigue, and tension overload. Failures can, however, be caused by combinations of these conditions if they are modified by the environment. As a rule, the type of failure is established by examination of the fracture surfaces and by comparing the operating conditions with available data on elevated temperature fractures. This analysis is usually sufficient for failure investigations. But when the operating conditions have caused a change in the metallurgical structure of the failed component, and it is possible that parts have been subjected to elevated temperatures, a more thorough analysis may be required. Most elevated temperature tests are accomplished by tension testing. However, in-service failures can occur not only by tension, but by bending, torsion, and compression types of loading as well. In many applications at elevated temperatures, distortion is also a serious problem. Creep can cause failure when a part under steady load has deformed or distorted so that it can no longer perform its intended function. The creep that occurs at any particular temperature generally shows 3 distinct stages, and these stages can be seen by plotting curves to show the percent of strain over time. There is first an elastic strain on the part or component. This is the immediate effect of the initial load. Following this initial elastic strain, there is a region of increasing plastic flow at a decreasing strain rate. This is the first stage of creep, the region called primary creep. Following the primary stage, there is a region of fairly constant strain rate. This is the second stage, the secondary or steady state creep. Finally, there is a region of drastically increased strain rate. This rapidly extends to fracture. This is the third stage or tertiary creep. The first stage of primary creep can be explained as an adjustment within the metal which occurs in the first few moments after the initial loading. Under this initial loading, the crystallographic imperfections begin to undergo realignment and the creep rate decreases. This leads to secondary creep. Second stage creep is an equilibrium condition between the mechanisms of work hardening and recovery. It is characterized by a constant but usually a relatively low creep rate. This secondary steady state creep is essentially a transition between primary and tertiary creep, even though it usually takes most of the time during a creep test. The zone for creep-resistant materials is a relatively straight line, and it is this fairly constant or steady state rate through the entire second stage that is considered to be the minimum creep rate. This is the rate widely used in engineering studies. Tertiary creep is the third and final stage of creep. The rate of extension increases and is followed by fracture. Tertiary creep occurs when the cross-sectional area of the metal decreases by necking or cracking, or both, and the creep rate accelerates. This creep rate will be increased by any environmental conditions that decrease the cross-sectional area. Tertiary creep may also result from metallurgical changes, such as recrystallization under load. Recrystallization promotes rapid deformation, accompanied by work hardening that is insufficient to retard the increased flow of metal. It is this rapidly increasing deformation that serves as a warning of fracture soon to occur. Sometimes metals do not exhibit all three stages of creep. For example, under conditions of high stress or high temperatures, the absence of primary creep is not uncommon. Upon initial loading, second stage creep or even third stage creep can begin immediately. At the other extreme, notably in cast alloys, only minimal third stage creep may be observed. Fracture may occur with minimum extension. A component subjected to creep loading in tension, torsion, or bending, or any combination of mechanisms, will eventually fracture, provided the strain occurring during creep does not relieve the stress. Stress rupture tests. Stress rupture tests are similar to creep tests. The difference is that the stress is often higher, the specimen may be notched, the test is much shorter in duration, and the principal information sought is the time to failure. Creep tests may last for months or even years, depending on the stress and temperature. Stress rupture tests generally last from about 200 hours to 2,000 hours. AMS specifications use higher temperatures and higher loads to obtain test times in the 24 to 48 hour range. Usually during a stress rupture test, the only data recorded are stress, temperature, time to fracture, and total strain. Depending on the alloy, the fracture by stress rupture may appear macroscopically as either ductile or brittle. Ductile fractures are transgranular and are typically accompanied by more pronounced distortion. A brittle fracture is usually intergranular and occurs with very little distortion. Intergranular cracking may not be readily discernible on the surface of a brittle stress rupture fracture. If the oxide is removed, the mode of cracking will usually be visible. The cracking mode is usually revealed in a polished longitudinal section. The cracking will frequently be seen below the fracture surface and parallel to the fracture surface. In fractographs, some stress rupture fractures exhibit both transgranular and intergranular fracture paths. In these instances, it is usually found that the transgranular fracture was initiated by a prior intergranular crack. The intergranular crack decreased the cross-sectional area and raised the stress. In general, brittle intergranular fractures are promoted by lower creep rates, longer rupture times, or higher temperatures. Other significant microstructural features are also associated with stress rupture fracture. When intergranular cracking occurs, the crack paths not only follow the grain boundaries at and beneath the fracture surfaces, the grains also appear equiaxed, even after considerable plastic deformation and total elongation. In contrast, transgranular fracture frequently exhibits severely elongated grains in the vicinity of the fracture. In tensile testing, the two common measures of ductility in the fracture are elongation and reduction of area. In stress rupture testing, the primary measures are true elongation at the end of the second stage creep and total elongation after failure. Despite some difficulties in the interpretation of ductility data, common practice is to plot elongation versus rupture life. for the nickel-base alloy S590 at a testing temperature of 1350 degrees Fahrenheit, the true elongation to the end of stage 2 shows a fairly straight line. Total elongation is indicated by an appreciable scatter of data points. At 1700 degrees, total elongation shows a similar scattering of data points. Therefore, true elongation generally provides the more accurate representation of ductility in metals at elevated temperatures. Stress rupture ductility is an important factor in alloy selection. In conventionally cast nickel-base heat-resisting alloys, for example, a stress rupture ductility of about 1% is common at 1400 degrees. The strongest wrought heat-resisting alloys have a stress rupture ductility of over 5%. Because component designs are frequently based on 1% creep, a low stress rupture ductility may preclude the use of an alloy to its full strength potential. The schematic creep curves for two alloys subjected to the same load and temperature conditions indicate that the higher rupture ductility means a higher safety margin. Premature failures have resulted from lack of ductility during stage 3. There is little warning of imminent fracture. In the design of components for service at elevated temperature, both strength and stress rupture ductility must be considered. Normally, these properties are determined quantitatively by smooth bar stress rupture tests. In most real-world service applications, components are subjected to complex stresses. These stresses include stress concentrations arising from inherent flaws in the metal as well as from design. And smooth bar tests do not account for these stress conditions. Fortunately, these conditions can be partly reproduced in the laboratory by the notched bar test. Notched bar stress rupture tests are of principal interest because the results show the relationship between stress rupture ductility and the ratio of notched bar to smooth bar stress rupture strength. Fatigue at elevated temperatures. In service, the steady loads or stresses to which components are subjected are often accompanied by mechanically induced cyclic loads. These cyclic loads are responsible for failure by fatigue. However, the precise relationship between temperature and fatigue strength varies widely, depending on the alloy, the temperature to which it is subjected, and the duration of the peak load. When parts and assemblies are loaded in combined steady state and vibratory loading, their fatigue behavior is complex. The anticipated life of a part subjected to simple creep loading at elevated temperatures decreases. The life of parts subjected to combined creep and fatigue loads decreases substantially. This effect must be considered in design and in failure analysis. Summary: types of elevated temperature failures. At elevated temperatures, stress produces a condition of continuous strain, creep. Principal types of failure are creep, stress rupture, low and high cycle fatigue, thermal fatigue, and overload. Type of failure is established by examination of fracture surfaces and by comparing operating conditions with available data on elevated temperature fractures. Creep occurs in 3 stages. Primary, the initial elastic strain. Secondary, the region of constant strain. And tertiary, increased strain extending to fracture. Fracture by stress rupture may appear as either ductile or brittle. Thermal fatigue. Mechanical conditions are not the only sources of cyclic loading that can cause fatigue failure. The cyclic effects of elevated temperatures can cause thermal fatigue. Temporary localized thermal gradients within a component can induce plastic strains. If these thermal gradients are applied repeatedly, the resulting cyclic strain can induce failure. The cracks caused by thermal fatigue usually initiate at the surface. They originate perpendicular to the surface and may occur singly or in multiples. The cracks then gradually propagate inward, usually progressing transgranularly. Because thermal fatigue cracks initiate externally, the amount of corrosion or oxidation varies along the fracture surface. The amount of corrosion or oxidation is inversely proportional to the depth of the crack. Oxidation in stress rupture cracks is more uniform. Excessive creep produces considerable distortion and numerous subsurface cracks. Thermal fatigue, on the other hand, produces little or no distortion and relatively few surface-oriented cracks. Typically, fracture surfaces of components cracked in stress rupture are irregular and discontinuous. In contrast, thermal fatigue fractures exhibit relatively flat, continuous surfaces. During service, the metallurgical structure of a part may be changed by the action of stress, time, temperature, and environment. The result is a change of strength. These changes are called metallurgical instabilities. The instabilities are indicated on the rupture life curve by a sharp change of slope. Sources of instabilities include transgranular intergranular fracture transition and aging or overaging. This involves precipitation or decomposition of carbides, borides, or nitrides. The principal metallurgical factor in stress rupture behavior is the transition from transgranular fracture to intergranular fracture. The temperature at which the transition occurs is called the equicohesive temperature, or ECT. The transition from transgranular fracture to intergranular fracture occurs because the properties of grain boundary regions differ from those of grains. At low temperatures, the grain boundary regions are stronger than grains. Therefore, deformation and fracture are transgranular. At higher temperatures, the grain boundaries are weaker than grains, so deformation and fracture are largely intergranular. The transition from transgranular to intergranular fracture occurs at the equicohesive temperature. The age-hardening alloys, which include certain stainless steels, aluminum, and heat-resisting alloys, among many others, are characteristically unstable when in a state of transition to the equilibrium condition. Under creep conditions, these age-hardening alloys usually continue to age with temperature-induced and stress-induced atomic migration. The result is reduced strength. At elevated temperature with stress, the submicroscopic precipitate tends to grow into a discrete phase large enough to become visible. The strains in the crystal lattice are minimized and the strength of the alloy decreases. The effects of environment. Environment and the interactions between surface and environment have a marked effect on the behavior of metals at elevated temperatures. In fact, the most common source of elevated temperature failure requiring premature replacement of a component is the environmental degradation of material. Environmental degradation of material causes far more elevated temperature failures than creep and stress rupture. In most elevated temperature applications, control of environment is essential, or the materials must be protected by coatings or self-protective oxides. Oxidation and all other reactions of metals with gaseous environments has long been recognized as a severe limitation to the utilization of metals at high temperatures. Therefore, the development of alloys for use at elevated temperatures is usually directed not only to improving the mechanical properties, but improving their resistance to hot corrosion as well. The alloys used in the hot sections of gas turbine engines are normally exposed to environments that promote corrosion and corrosion erosion. Consequently, these alloys are selected for high strength and resistance to surface degradation. But as the designs of gas turbine engines are constantly changed to improve efficiency, the gas and metal temperatures are necessarily increased. Maximum temperatures, however, are limited primarily by the high temperature strength of the alloys used for turbine applications. Hot corrosion is one of the most serious problems with gas turbine engines, boilers, oil-fired furnaces, and other units operating at elevated temperatures. Hot corrosion is accelerated by the presence of sodium chloride and sodium sulfate, which are usually present when assemblies are operated near seawater. The main sources of sodium compounds are the sea salt in the air and the fuel used in the engine. Salt-containing atmospheres at elevated temperatures have a universally corrosive effect on almost all metals. Steel, stainless steels, heat-resisting alloys, and titanium included. As a rule, the adverse effects of salt increase as temperature increases. Significant advances have been made in the development of alloys with better resistance to hot corrosion. Still, the most effective method of minimizing hot corrosion and preventing premature failure is the use of protective coatings. These coatings supplement the inherent corrosion resistance of most heat-resisting alloys. However, at best, they provide only a partial solution to the hot corrosion problem. An uncoated turbine blade after 118 programmed cycles shows severe degradation by hot corrosion. The same nickel-base alloy with a nickel aluminum protective coating after accelerated hot corrosion testing in an engine is only slightly degraded. The aluminum-rich coatings, such as the aluminide coatings, successfully extend the life expectancies of gas turbine engine blades and vanes. Another class of high-temperature corrosion-resistant coatings is applied to surfaces as complex cobalt-base alloys. The coatings are applied by electron beam vapor deposition or low-pressure plasma spraying. Hot corrosion can also attack a coating in a localized area. A localized attack may be the result of variations in the chemical composition of the coatings. The attack can also be the result of corrodants concentrating in a localized area. It is also possible for corrosion-erosion degradation of the coating to occur at one specific location. A good example is the leading edge of a turbine blade, which is exposed to high-temperature, high-velocity gases in the turbine. Subsequently, the base metal is also attacked, requiring premature removal of the component from service. In an oxidizing atmosphere, aluminide coatings form a protective aluminum oxide layer on the blade's surface. The cyclic operation of a gas turbine engine causes the oxide to spall off. Subsequently, the coating forms another protective layer of aluminum oxide. The process is called self-healing. Controlled carburization is the diffusion of carbon into the surface layers of steel. Controlled carburization is a widely used and useful heat treating process to develop high surface hardness in the steel. Uncontrolled, the carburization can be highly detrimental to components in service at elevated temperatures. Unwanted carburization is common to many industrial applications. With or without oxidation, the carburization takes place in resistance heating elements and various components and fixtures of heat-treating furnaces. Certain petrochemical plant components, such as heater tubes, may also be subjected to carburization or oxidation, or both. Both oxidation and carburization can be highly detrimental to components at elevated temperatures. The two processes generate volume changes that are non-uniform. These volume changes result in very high residual stresses within the part or component. In addition, there may be a loss of metal by corrosion erosion or embrittlement by the carbon pickup, which forms carbides. Ultimately, the corrosion or the corrosion erosion results in a loss of supporting thickness in the structural member. Carbide formation results in a loss of ductility and makes the component susceptible to brittle fracture. Heavy carburization also eliminates the possibility of repair welding. In stainless steel, the diffusion of carbon results in the formation of additional carbides. Before the unwanted carburization, the microstructure of a stainless steel consists of small carbides restricted to the grain boundaries. In service, the same steel shows massive islands of carbides formed in the austenite matrix. Carburization of stainless steels also contributes to embrittlement. A high volume of carbides produces an increased susceptibility to attack by oxidation. The attack occurs when metal surfaces are simultaneously or intermittently exposed to heavily carburizing and oxidizing environments. The condition is sometimes referred to as green rot because it creates a distinctive green surface condition. Under these conditions, the dual action of carburization and oxidation can weaken the metal. Oxidation attack occurs at the grain boundaries. The loss of grain boundary strength is followed by detachment of grains and subsequent erosion. Now, before we demonstrate how the various causes of elevated temperature failures are related to industrial applications, let's review and summarize. Thermal fatigue is caused by mechanical stress, brought on by uneven thermal and contraction stresses. Thermal fatigue produces little or no distortion and relatively few surface-oriented cracks. Cracks propagate inward, usually progressing transgranularly. The principal causes of failure at elevated temperature are corrosion, hot corrosion, and uncontrolled carburization. Hot corrosion is oxidation. Elevated temperature failures in industrial applications. Gas turbine engine components are made of a variety of metals to accommodate operating temperatures ranging from ambient to above 2200 degrees Fahrenheit. Hot parts, such as burners, turbine blades, and vanes, are designed for high strength at elevated temperatures. Nevertheless, in all of these specially designed and alloyed parts, creep is a problem. Rotating components can stretch, often beyond limits, causing them to make contact with nearby stationary components. The result is rubbing deformation and failure. Fatigue is a fairly common cause of cracking in turbine blades and vanes. Fractures originate from the highest stress locations or from critically located defects. Fatigue fracture can also originate at notches caused by FOD, which is short for foreign object damage. FOD decreases the effective cross-sectional area, and the subsequent fracture is usually due to ductile tension overload. There have been instances of large jet engines swallowing small planes, foreign object damage in the extreme, perhaps. But birds and miscellaneous flying objects are a constant threat to jets. Components of the burner section are susceptible to thermal fatigue cracking. Like fatigue cracking, thermal fatigue cracking also produces cracks that may be difficult to distinguish from those produced by creep and stress rupture. This is due to oxidation of the fracture. Among the other types of burner component failures encountered are distortion, extreme oxidation, and melting. Failure by liquid metal. Several kinds of elevated temperature failures can occur by contact with liquid metal. In general, liquid or molten metals used in coating other metals cannot be contained in vessels made from heat-resisting alloys. These coating metals include aluminum, zinc, and copper. Molten lead can also be used to coat metals, provided the lead bath for the coating is covered with a protective layer of powdered charcoal. When molten lead is not protected from air, a lead oxide forms, and this oxide is highly corrosive to most heat-resisting alloys. Among the alloys that have been used successfully to contain molten lead, however, are Inconel 600 and RA 333. Fracture associated with contact by liquid or molten metal is usually compounded by liquid metal embrittlement, which weakens the grain boundaries. For hot dip galvanizing, tanks that contain the molten zinc are commonly made from low-carbon steel plate, which normally provides acceptable life. Many steel parts are protected from atmospheric rusting by a thin electroplated cadmium layer. However, if cadmium-plated parts are heated above 600 degrees Fahrenheit, as they are in welding, brazing, and soldering, the cadmium can penetrate the grain boundaries, and the result is cadmium embrittlement. A similar liquid metal embrittlement is caused by mercury and indium. Failures of furnace parts. Among the parts subjected to the most severe service at elevated temperatures are the components and related fixtures used in heat-treating furnaces. The life of radiant tubes used in carburizing and carbon nitriding furnaces generally varies from 6 to 20 months. Their life depends largely on their alloy composition, the composition of the fuel being burned, how the furnace is operated, whether it is cyclic or continuous, and the positioning of the burners. One of the better proven alloys for radiant tubes in a carburizing or carbon nitriding environment is a nickel base Ra333. The life of heat-resisting alloys in contact with molten salts is usually erratic. For example, thermocouple protection tubes under similar service conditions may survive 100 immersions before replacement is necessary. And then again, they may fail after only 5 or 10 immersions. The components exposed to molten salts usually fail by perforation or by structural disintegration. Intergranular attack related to chromium depletion at the grain boundaries often contributes to the failure. Failure is sometimes related to variables in the operation of the furnace. For instance, the control of temperature may be lax. Hot spots can exist in the furnace, and sludge can accumulate, all of which may affect the components within the furnaces. The salt pots used in heat treating applications are also subject to erratic service. When heat treating fixtures are subjected to temperatures above 1200 degrees Fahrenheit, they will have a limited life. As operating temperatures increase, their life shortens rapidly. Also, when fixtures are repeatedly quenched, their life expectancy is decreased even more. Fixtures usually fail by a combination of thermal fatigue, oxidation, carburization, and warping. With repetitive heating and cooling, fixtures always face the possibility of failure by thermal fatigue. Trays and baskets and fixtures used for holding workpieces during carburizing or carbon nitriding operations may become carburized and fail prematurely. One of the better alloys for such service is cast H heat-resisting alloy. When subjected to both cyclic quenching and a carburizing atmosphere, the fixtures with heavier cross-sections are more likely to fail as a result of thermal fatigue than as a result of carburization. Macrographs of Ra333 alloy bars taken from the same furnace basket show the effects of carburization. The smaller bar, 3/8 of an inch in diameter, shows no evidence of cracking. The half-inch bar exhibits severe cracking by thermal fatigue. Failure due to carburization generally occurs at room temperature, when the component embrittled by chromium carbide breaks as a result of impact or jarring. This type of fracture usually originates near the central portion of a fixture, basket, or tray. Failures of engine exhaust valves. The exhaust valves of internal combustion engines are subjected to elevated temperatures along with high repetitive loads. Among the types of failures encountered in valves are those caused by the rapid oxidation of hot gases, fatigue, thermal fatigue, corrosion, erosion, overstressing, and combinations of these factors. Burning is the most common mode of valve failure. The burning results in large grain size and oxidation of the grain boundaries. The next most significant failure mode is fatigue. Fatigue generally occurs at the junction of the stem and head, the point where hot gases from the combustion process impinge on the valve stem during the exhaust cycle and create a notch effect. Temperatures in this area normally range from about 1350 to 1400 degrees Fahrenheit. Mechanical forces from firing pressure and valve spring pressure provide the stress for failure. The fracture surface of a typical valve stem failing by fatigue shows multiple crack initiation points. The crack propagated by fatigue through 3/4 of the stem before the final fast fracture occurred in a single cycle. The source of stress concentration was a geometric notch resulting from a crack caused by oxidation. It is possible that the failure of exhaust valves and many other parts may be caused by problems in other sections of the assembly. For example, exhaust valve failures sometimes result from inadequate cooling by the cylinder head. Excessive wall thicknesses, blocked coolant passages due to cracked cores and other foundry problems are usually located by sectioning the cylinder head. It is also worthwhile to determine if the coolant was circulating properly through the radiator, water pump, hoses, thermostat, and other parts of the cooling system. Problems in the cooling system particularly can affect other parts in the assembly. Testing techniques. The investigation of failures at elevated temperatures, to a large extent, follows the general procedures for failure analysis. Much of the standard equipment can be used. There are some special testing techniques, however, and these are generally highly complex and specialized. Frequently, the only way to find an answer to the elevated temperature problems is by simulated service testing. Simulations are helpful in reconstructing failure under carefully controlled conditions. Many of these simulated service tests have been developed for solving the problems of gas turbines, which present some of the most rigorous high-temperature demands of any industry. Magnetic tests are widely used for analysis of failures involving normally non-magnetic heat-resisting alloys and austenitic stainless steels. Many of these alloys become magnetic as a result of alloying element changes caused by oxidation or carburization, or both. Consequently, when nickel-containing alloys and austenitic stainless steels show evidence of magnetism, some insight into the possible causes of failure is provided. Macro etching of cross-sections is another simple test. Macro etching is useful in detecting the cracks and voids characteristic of thermal fatigue failures. When thermal fatigue is severe, sectioning will reveal the characteristic signs. Metallographic examination is helpful in detecting microstructural changes and corrosion products associated with common modes of failure. Once detected, the microconstituents and corrosion products can then be identified more positively by chemical analysis, X-ray diffraction, or electron microprobe analysis. Tests for low cycle thermal fatigue and creep can be conducted on the Ferris wheel disc. This testing apparatus subjects full-scale gas turbine engine discs to simulated low cycle fatigue conditions. A special type of non-destructive inspection is used to show the first indication of a crack. Oxidation corrosion burner rigs have been developed to test turbine blade alloys and coatings. These test rigs are capable of testing 8 to 12 specimens under engine conditions at temperatures from 1450 to 2300 degrees Fahrenheit. The basic steady-state oxidation test simulates aircraft cruising conditions. Higher than cruising temperatures are obtainable to accelerate degradation. These are just a few of the tests available for detecting and simulating failures that can occur at elevated temperatures. It should be said, however, that even though testing equipment to simulate conditions of elevated temperature service is necessarily sophisticated and specialized, the service conditions of elevated temperature applications, the basic causes of failure and fracture, are still much the same as those encountered at any temperature. In the analysis of these failures, however, we must take into account the fact that reactions between metal surfaces and their environments are accelerated at elevated temperatures, and this can result in a variety of special problems. Elevated temperatures can cause a variety of metallurgical instabilities, and the problems caused by elevated temperatures are very real concerns in many industrial applications. Yet the major types of elevated temperature failure are relatively basic in failure analysis: creep, stress rupture, fatigue, thermal fatigue, distortion, carburization, and oxidation.